Hello everyone. We will now begin our lecture on section 5 of chapter 8, which is on transformational geometry, symmetry and tessellations. Now in transformational geometry, we will learn how we can move a shape, a figure from one position to another position without changing its form, without changing its shape or its size. We'll talk about how to reflect a figure, that means get a mirror image of the figure across a certain line. We will talk about maintaining symmetry of different figures, and tessellations essentially refer to creating mosaic patterns from different geometric shapes. All right. Other than mathematicians, these topics are of great interest to artists, architects, as well as graphic designers. All right. So these are the different topics we will learn in this section. As part of transformational geometry, we will learn how to perform reflections, translations, rotations, and light reflections of geometric figures. Then we will talk about identifying symmetries of geometric figures. And finally, we will be able to identify tessellations of geometric figures. Let's understand the definition of transformation, also known as rigid motion. It is the act of moving a geometric figure from some starting position to some ending position without altering its shape or size, and that is what rigid motion or transformation is. So here we have over here at the bottom a trapezoid figure marked A, B, C, D, and they've moved it up above and they have relabeled it as A dash, B dash, C dash, and D dash. So as you will notice that they haven't changed the shape or the size or the form of this figure. They have just moved the figure as if they have forklifted it and placed it somewhere as is. So that is what transformation is about, and we will learn how we can perform that transformation. Another kind of transformation is called reflection. A reflection is a rigid motion that moves a geometric figure to a new position such that the figure in the new position is a mirror image of the figure in the starting position. So as you know, we talk about reflection across a certain position. So when you look at a mirror, you see your reflection across the mirror. If you are looking down at clear water, you can see your reflection across the surface of the water, correct? And that surface, whether it's that of the mirror or across the surface of a lake, is called the reflection line or the axis of reflection. So again, I'm going to read through it. A reflection is a rigid motion that moves a geometric figure to a new position such that the figure in the new position is a mirror image of the figure in the starting position. In two dimensions, the figure and its mirror image are equidistant from a line called the reflection line or the axis of reflection. So if we have our axis of reflection, let's say this is the mirror or the surface of the lake, and something is being reflected, this point is getting reflected, then in the process of reflection, you will see that point same distance from that surface across. All right, so that's what they are trying to say here when they say that it'll be equidistant from a line called the reflection line. So here is the reflection line, and if this is what you are reflecting from the right and the reflection is on the left, then it'll be positioned equidistant from the line of reflection or the axis of reflection. Now the first example is about reflecting a triangle across the line of reflection, this axis of reflection. So keep in mind we have to apply the rule of points being equidistant from the axis when we reflect them across the line. So if A is positioned 2 units to the right from the line, then it should be reflected exactly 2 units to the left of that line. Same for B and C. So we are going to go on to the next slide to see how that transformation is performed. Now the first example is an exercise of reflecting a triangle across a line of reflection. So we have a figure here on the right hand side which is a triangle ABC, and the line of reflection is labeled I, and we are going to reflect this triangle across on the other side. That means across to the left of this line of the axis. All right, so we're going to obtain a reflection and label it A dash, B dash, and C dash. Now, by the rule of equidistance, the point is going to be reflected exactly the same distance from the axis to the left. So currently on the right hand side, point A is located 2 units to the right. When we reflect it, it's going to be exactly 2 units to the left. Point B is 1, 2, 3, 4, 5, 6 units to the right. The reflection of point B, B dash, is going to be exactly 6 units to the left as well. As far as C is concerned, 1, 2, 3, 4, 5, 6. C is located exactly 6 units to the right. When we reflect that, it's going to be 6 units to the left. All right. So let's look at the solution step by step, what they say here. Point A is 2 units to right of I. So it should be the reflection A dash should be 2 units to the left of I on the other side of the axis. Same for point B, which is at 6 units to right of I, will be reflected 6 units to the left of I. And then point C is 6 units to the right of I. It should be reflected 6 units to the left of I. All right. Now, once you reflect each of these points from the right to the left and connect the points, you will get a reflection of the entire triangle. So recall that the points should be equidistant across from the axis. So it was A was 2 units to the right. It's reflected and drawn exactly 2 units to the left. Same for B, it was position 6 units to the right, so B dash is exactly 6 units to the left, and C dash, which was positioned 6 units to the right, is now positioned 6 units to the left. And once we connect the figures, all right, once we connect, well, not the figures, once we connect the points, we get a reflection, a mirror image of the triangle on the right. All right. Now, another kind of transformation is called a translation or glide, which is a rigid motion that moves a geometric figure by sliding it along a straight line segment in the plane. The direction and length of the line segment completely determine the translation. In other words, it is repositioning a figure from one place to another place. All right. So let's say we have a square figure. Let's take a square figure this time. All right. So it is currently positioned here. If we want to push it to the left and position it somewhere here, we've performed a translation. All right. Again, without changing the shape or the size of the figure. All right. So this is not really the same size, but keep in mind that in a translation, the size, shape should be same. All you're doing is repositioning the figure. So you could reposition it horizontally. You could either push it and move it to the left, or you could push it from the left and move it to the right, or you could move it up and down, vertical translation. So translations can be vertical translations. It could be horizontal translations. Vertical would be moving it up or down. Horizontal would be moving it to the left or to the right, or it could involve both. That means we could move it down and then to the right, or up then to the left. So it's a combination of translations, moving it up, left, up, right, or down, left, down, right, a combination of them. All right, so we will learn through an example how we can perform a translation, but all through remember that the shape should be the shape, the size of the figure should not be changed. Now, one way to express a translation is by using a translation vector. Translation vector is nothing but an arrow which indicates not only the direction in which the figure is going to move, but it also tells the distance that a figure is going to be moved along. All right. So it's usually indicated like this. All right. So you have a square here. This figure is expected to be translated. All right. So we can use a translation vector which is along the same horizontal line, and then we can draw an arrow from that starting point over here, all right, somewhere here. So this is the translation vector. This arrow is what's called the translation vector, all right, and this vector is showing that move it so many units to the right and then so many units down. So if this is position A, all right, if this is point A, then based on this translation vector, it tells us that move it one, maybe, there are grids. Just imagine there are grids in here. Then 1, 2, 3 units to the right, and 1, 2, 3, 4, 5 units down. So this translation vector gives us two pieces of information: how many units to the right or to the left, and how many units down we are going to shift the figure. All right. So here's an example of translating a square figure to a different position. Now, to what position it will be moved, it will be translated, will be obtained from this vector, translational vector provided to us. All right. So we see over here this vector is an arrow essentially, with its initial point at with this indicated by this dot here, and then it extends up to a certain point and terminated by the arrowhead, and it's indicated by VV for vector. That's the letter or the convention we use to label a vector. So what does this vector tell us about the new position of this figure? You see, this initial point is how many units to the right of B. All right, so it's 1, 2, 3 units. So this tells us that the figure should shift 3 units to the right, 1, 2, 3. And then it should go 6 units down. So 1, 2, 3, 4, 5, 6. So this arrowhead is 6 units down from the initial point. All right, so what's going to happen is the whole figure is going to shift 3 units to the right and 6 units down. So we have over here A. All right, point A is going to shift first 1, 2, 3 units to the right, and 1, 2, 3, 4, 5, 6 units down. So the new position of A, let's count again: 1, 3 units, and then 1, 2, 3, 4, 5, 6 units is here. So this is going to be the new location of A, and then the positions of B, C, and D are going to be changed in the same manner, correspondingly. So here is the translated square. All right, it will have the same size and shape. The size and shape should be unaffected by the translation, right? And the translation vector points 6 units downward and 3 units right, as we saw in the slide before. And that's exactly what happens. A moved 1, 2, 3 units to the right, and then from its current position 6 units down. So 1, 2, 3, 4, 5, 6 units down. So that's the new position of A, which is marked as A dash, and then all the other points are shifted correspondingly. So B was uh, 1, 2, 3, 4 units to the right of A. It still remains 1, 2, 3, 4 units to the right. C was 1, 2, 3, 4 units down from B, and that's how it stays, 1, 2, 3, 4 units below B. B dash in this case, and in a similar way we position D dash, and we get the new figure A dash, B dash, C dash once we connect the point. So once we get the first position, the first point position correctly, all the other points will take their position with reference to A, or A dash in this case. All right. So here's a final look at the translated square. Over here again, to repeat, A has moved 3 units to the right and 6 units down from its original position, and then the other points moved correspondingly with reference to point A dash, and once we connect the points we get the square, the translated square. However, the shape, of course, the shape doesn't change, neither does the size. All right. Now we will talk about another kind of transformation or a rigid motion called rotation. All right. Now, an application of rotation you've seen on your devices. When you look at your pictures on your phone, you may have seen, or you want to edit it, you may have seen an option which looks like this with an arrow, circular arrow. And if you click on it, then it keeps turning the photo. Every time you click on it, it'll turn the photo by 90 degrees, correct? So if you have your picture like this, right? Let's say you have your picture here, and you click on it once on this arrow. So this is rotating clockwise, correct? The way a clock goes around. So it's clockwise rotation. If you click on it once, what happens is it rotates 90 degrees. So that means, let's say this, we'll just mark the ends of the picture as A, B, C, D, and let's say that this is the picture of a person. When we rotate it, what happens is it becomes like this. It rotates, all right, and the A that was here now goes like this, the B goes down, the C is here, and D comes here, right? So this is a 90-degree rotation. If you click on, so this is, and let me take on my pointer at this point. This is a 90-degree rotation. If you click on it again, it'll move another 90 degree. That means 180 degrees from the initial position, correct? So how will the picture look like in that case, right? It will look like, it'll look like this, right? Only thing is you will now be upside down, or whoever is in the picture will now be upside down. So what happened is A comes here, B comes here, C comes here, and D comes here. All right. Whereas over here, when we rotated it 90 degrees, this is how the picture looked like. All right. Okay. And then if you rotate it, or I mean you click it again, it'll rotate it another 90 degrees and it'll take this position. All right. 270 degrees. So it'll again be like this. Only thing is A is going to be here, B going to be here, C going to be here, D going to be here, and you're going to, or this is how the picture is going to look like. And if you click it another time, it's going to rotate back to its original position, right? It's going to come back to this original position. So I guess this example will help you relate to what rotation is about. All right. So let's just read through it. It says a rotation is a rigid motion performed by rotating a geometric figure in the plane about a specific point, called the rotation point or the center of rotation. So that rotation is done with reference to a rotation point or the center of rotation. The angle through which the object is rotated is called the angle of rotation. So when we clicked on it once and it rotated by 90 degrees, that's the angle of rotation. If you clicked on it twice, the angle of rotation would be 180 degrees. All right, and then 270 degrees, and then back to the original position, but it would have rotated 360 degrees, right? So let's look at this example of rotation. The rotation point is inside a parallelogram, and that point is marked as P, and the ends of the parallelogram marked as A, B, C, D. So let's see what a 90-degree rotation would look like and a 180-degree rotation would look like. However, the rotation would also factor in the direction, whether you are rotating it clockwise or whether you're rotating it anti-clockwise or counterclockwise. All right. So here we are rotating the figure 90 degrees counterclockwise. That means in the opposite direction that a clock runs. So the original figure was placed horizontally, so A was positioned here, B, C, D. When you rotate it counterclockwise, the A comes to the bottom. All right, if you rotated it clockwise, A would go up here. All right, but because it's counterclockwise, you start going in the opposite direction, so A becomes A dash, it comes down 90 degrees. And what's the next one? D comes here, all right, and then C and then B dash. All right, so let's look at the solution. It says horizontal line segments will be vertical line segments. What was horizontal? That's AB. It was horizontal. Now it becomes vertical, and the vertical one becomes horizontal. That's how it works. So vertical line segments will be horizontal line segments, whereas horizontal line segments will be vertical line segments. So in the original parallelogram, the line segment AB, which was 1 unit above P, now becomes the line segment A dash B dash, which is 1 unit left of P. All right, so that is how the 90-degree rotation works. So what would 180 degrees counterclockwise rotation look like? The horizontal line segments will still be horizontal line segments, and the vertical line segments will still be vertical line segments. However, the labeling would be different. So it'll be A, D, C, B. All right. So what happens with the 180-degree counterclockwise rotation? Vertex A double dash is in the same position as vertex C of the original parallelogram. So let me just quickly draw the original parallelogram. Then this is how it looked like. In the original parallelogram that we have been rotating, A was here, B was here, C was here, D was here, right? So what happens now when we rotated it 180-degree counterclockwise, we see that other than the vertex labels the position of rotated parallelogram, A dash, B dash, C dash, and D dash is the same as the position of the original parallelogram A, B, C, D. All right, so it's actually in the opposite along the diagonals, right? A was here. When we rotated it 180 degrees, A dash goes to the other corner, the diagonally opposite corner. Likewise, D, all right, D was here in the original figure. When we rotated it 180 degrees, D goes to the other end, diagonally other end of the parallelogram, and the same with B, all right, B and C as well. Now, another kind of transformation or rigid motion is a combination of two movements, all right? So it's called glide reflection. That means it's combining translation as well as reflection, all right? So it's combining two motions together, and so it's not only inverting, reflecting the figure, but it's also changing its position. So a glide reflection is a rigid motion formed by performing a translation or glide followed by a reflection. In a glide reflection, the reflection line and the translation vector must be parallel to each other. Now, what do we mean by symmetry? A symmetry of a geometric figure is a rigid motion that moves the figure back onto itself. That is, the beginning position and ending position of the figure must be identical. To make this simple, let me just tell you what symmetry is. It's just you take a figure, and if you draw a line through the center, whether horizontally or vertically, you will have two equal halves. All right. So look at this figure here. All right. So if I draw a U like this, all right. If we were to draw a line through the center of this figure, of this U, then we will get two the two sides. If you fold these two sides, let me take out my pointer. If we fold these two sides upon each other, they will overlap, exactly overlap. All right. So that's what symmetry means. The beginning position and ending position of the figure must be identical. That's what essentially it means. So in any symmetrical figure, if you draw a line through the center, it'll be equal halves. All right, it'll be a replica. One side will be the replica of the other. So in the same coin, there's another form of symmetry called the reflective symmetry. And what it is if we have, and I'll use the same example that I used before, we say we have this U-shaped figure. Now this was my starting point, and this was my ending point. All right, and I'll draw a line through its center, and we see that that line cuts it into two equal parts. And if I were to fold this, all right, if I were to fold it, then what would happen is this end position would coincide with the starting position, right? This is the starting position, this is the ending position. If I fold it, then they will overlap. It's exactly onto each other. So the starting position and the ending position would fall on each other. So that's what reflective symmetry is. If we use rigid motion reflection about line I, so let's call this line that I drew through the center of this U figure, and the ending position is identical to the starting position. Although vertex labels are different, we say that the polygon has reflective symmetry about line I. We refer to line I as a line of symmetry. All right, it's also called the axis of symmetry. So this is how reflection about line I looks like, an example of that. We have a star-shaped polygonal figure labeled A, B, C, D, E, F, G, H, and the line of symmetry or the axis of symmetry passes through the points A and E. So if we were to reflect each of these points across this line, that means reflect D across this line, it would be in the position of F, and F would come to the position of D. C would go to the position of G, and G would go to the position of C. B would go to the position of H, H to the position of B. We would get back the same shape. There would be no change in the shape, and that's what reflection about a line means. All right. Now to talk about rotational symmetry, this is similar to rotational transformation that we learned before. It says here if we rotate a polygon about a point P and the ending position is identical to the starting position, although vertex labels are different, we say that the polygon has rotational symmetry about line I. We refer to point P as a point of symmetry. So without trying to explain this, I'm going to go to the next slide, which has an example, and I think it'll be more clear if we try to understand rotational symmetry through an example. So again, we have this star-shaped figure with the points labeled A, B, C, D, E, F, G, H, and there's a point at the center P about which we are going to rotate it counterclockwise 90 degrees. So rotation of 90 degrees about point P, and this is the point at the center, and it's going to be rotated counterclockwise. They should have mentioned that, because otherwise it would be a little bit different if we rotated it clockwise. So counterclockwise is how we are going to rotate it, or how the example is rotating it. All right. So what happens is when we rotate it 90 degrees about this point, that means this A is going to go and sit where G is. All right. G is going to turn and rotate and sit where E is. E is going to take the position of C, and C is going to take the position where A was. All right. And that's what we see in this figure. So originally A was on top. Now A comes to the left. It has rotated about this point 90 degrees. So let's draw this here. So A was originally here. So when it rotated 90 degrees, it came and landed here. Likewise, G, which was here, came to the bottom. All right, it rotated 90 degrees. Same with E and C. And then we will be rotating these points, inner points B, H, F, D in the same manner. F will take the place where D was. D will go up to B's position. B will go up to H's position, and H will take F's position. All right, so this is an example of rotation or rotating 90 degrees counterclockwise about point P. Now, as far as tessellations are concerned, we will understand what it is and then look at some examples, all right? So a tessellation or tiling is a pattern consisting of the repeated use of the same geometric figures to entirely cover a plane, leaving no gaps. The geometric figures used are called the tessellating shapes of the tessellation. So it's a mosaic pattern formed by putting together several polygonal shapes and creating an artistic design, so to speak. All right. So let's look at some examples of. Here is a simple tessellation made from triangles, putting together triangles. This is a mosaic pattern, and then we have one with squares as well. We have seen tiling done on our kitchen walls or bathroom walls or even on the floor. Those are all examples of tessellations. Here's another tessellation made by putting together hexagonal shapes, correct? Now, tessellations are commonly used in the area of art, architecture, on ancient buildings, temples, churches. We see decorations done with tessellations and geometric shapes. So here's an example of a tessellation from ancient Egypt, but it is very common. That's how buildings used to be decorated in olden times, putting together or creating mosaic patterns from different shapes. All right.